So when we have waves in 3 dimensions, like we have in an atom, we need 3 quantum numbers to describe their orientation, their shape, their size, and their energy. But there is a 4th quantum number, and it has to do with a quantum mechanical property that electrons have. And it's called spin. If you picture the electron as though it were a little sphere, and we're looking at it from overhead, maybe it could be spinning clockwise, or maybe it could be spinning counterclockwise. And because it's a moving charge, there will be a magnetic field that's associated with it. This rotating charge will have a magnetic field. And the magnetic field in this case will go opposite the direction of this one. So we could distinguish between 2 electrons. There could be a spin-up electron, or there can be a spin-down electron, depending on which way it's spinning. And this is the terminology that they use. 2 kinds of electrons, spin up or spin down. So here's a classic experiment that discovered this property, spin. If you take atoms with an odd number of electrons, originally they used silver atoms. Later on, shortly after that, they used hydrogen atoms. Hydrogen has 1 electron, so it'll work in this experiment. Focus them into a beam. And now you're going to send them through a magnet. Now, the idea here is that if the spin-up ones are going to interact with the magnetic field one way, and the spin-down ones will interact another way. The magnet looks a little bit weird because you need to have a non-homogeneous magnetic field to do this experiment. In other words, the magnetic field has to change in a certain way. So the top pole of the magnet is shaped like a tab, and the bottom magnet is shaped like a groove. So say this is the North Pole and this is the South Pole. As the beam goes through this non-homogeneous magnetic field, the spin-up electrons will veer one way, and the spin-down electrons will veer another way. And you'll get 2 distinct signals out of this. The beam will split in 2. This detection of electron spin, let's say this is the discovery of electron spin, is called the Stern-Gerlach experiment. You may see it referred to this way. So you can have spin-up electrons or spin-down electrons. Now there's a quantum number that goes with that. If you do the spin-up, they have a quantum number called m sub s. And its value is 1/2. So unlike all the other quantum numbers, this quantum number can be a fraction. And if you have spin down, that has a value of -1/2. Okay? And these are the only 2 values that are possible, and they don't depend on any of the other quantum numbers. So m sub s can be either +1/2 for electrons or -1/2 for electrons. So this 4th quantum number gives us a way to address electrons. We can take an atom and we can assign quantum numbers to its electrons. Let's try a hydrogen atom. And what are the quantum numbers that we know now? The principal quantum number, the orbital angular momentum quantum number, the magnetic quantum number, and the one we just did, the magnetic spin quantum number. So what's the lowest value that we can start off with here for n? Well, the first value of n is 1. You can't start it with 0. Alright, so what's the L value that goes with that? Well, L can be anywhere from 0 up to n minus 1. 1 minus 1 is 0, so it's got to be 0. So basically what we have here is a 1s subshell. 1s is the code for L equals 0. Now what are the m sub L values that I'm allowed to have? Well, they can go from minus L up to plus L. So they can go from minus 0 up to plus 0. Just 0 is the only one that I'm allowed to have. So there is one orbital in the 1s subshell because there's only one value of m sub L. Now, how about the electron that's in there? It could be either spin up or spin down. Let's say it's spin up. So what I've got here with the story that these things are telling me is that I have a 1s subshell with one orbital in it. That's all that's allowed. And it's got a spin up electron in it. Now, this is a lot of detail. So what I could do is condense this a little bit. Let's draw a circle that is the orbital. It represents the orbital. And you can think of the orbital as a little container now that can hold electrons. And I'm going to label it 1s. So there's one orbital, 1s. And now it's got a spin up electron in there, and I will symbolize it like that. This is the same information as I have up here. I am representing it in a different way. When I write it down this way, it's called an orbital diagram. So listing the quantum numbers out this way is the same thing, giving me the same information that I'm getting from my orbital diagram here. It's a lot easier to look at this, though, than it is to look at all that. Now, to see how this works, let's do another atom. Let's do helium. Helium's got 2 electrons. So the first electron will be just like the hydrogen electron, so I'm going to keep this electron address. And you can think of this as an address for that first electron, or a pin, a name, an address. It's kind of like an address because it's like you're in the first shell. You're in the 1s subshell. You are in the one orbital that is inside the 1s subshell. And you have a spin-up electron in there. So it is like an address. What's the address of the second electron? Well, I can fit another electron in there. If I have these 3 the same, it is possible for me to have another electron in there. Now, every electron has got to have a unique address. That is a unique set of 4 quantum numbers. These 2 electrons have slightly different addresses. It's kind of like they're roommates. They're both in the same orbital. One spin up and one spin down. Another way that I can say this is that every orbital can hold a spin up and a spin down electron. So there's a total of 2 electrons that you can fit into an orbital. These 2 statements are called the Pauli principle. I would know that name. It's referred to by that name. This is going to help us build electron configurations. What we're going to try to do is build an electron configuration for an atom, which is kind of a seating diagram. It shows you where all the electrons are and what they're doing too. And that's going to give us some insights into why different elements act the way that they do later. And it is also going to tell us why the periodic table is shaped the way it is. So that's where we're going with this eventually. Now we can build up these orbital diagrams by tediously listing all of the quantum numbers for each electron. But later on in the next lesson, we're going to see that there's an easier way for us to write down orbital diagrams for atoms.